Okay, so welcome to lecture number 7 in network security. So the last time we have introduced the tunneling approach, how you can connect a network across various sites, maybe to do it somewhere else. So the main aim was to allow basically to connect various sites as if they would be in the same domain, in the same place, that all of the broadcasts that are emerging at the MAC layer, for example, are reaching also the other sites through the unsecure, potentially malicious internet. So they virtually will act as if it would be one network, so therefore it's a virtual private network. And the core example is always you have your printer, you have a file server, and you can find them through simply sending messages to the other side. And one further approach is if you have external home office workers where you do not have, which basically switch their positions, switch their internet connectivity, switch their connection to the internet, they can also associate to that network. So here at the university we use that as well, for example, to access specific servers that are not accessible from the internet, just only from within the network. So typically you have here also some kind of firewalls that prevents the access to specific systems from the internet. But if you have a VPN tunnel, then you act as if you would be in the network itself, and then you can access them. And then we came to we had a look at how this is eventually realized. So typically you have some kind of router of some kind of machine, and this machine exposes this tunnel in software as a potential new line to send messages through, and all packets pushed into this line will be encrypted and sent to the endpoint that is designated, that has been configured for basically being the tunnel endpoint. So on the sender side, you have the option to choose basically various output lines, and one of them is this, you have a real network interface and you have a virtual network interface, and those packets sent to the virtual network interface will be encrypted, will be processed through software, and sent over the real network interface later on. And the recipient side, so there the messages from the encrypted messages arrive. They are associated to the virtual private network software and decrypted at that side, so and then released in the intranet again at the recipient side. So, and eventually we have stopped at the point at what protocol to use below a virtual private network, and as everything is encrypted, and sorry, wrong button. Everything is encrypted, so typically you have the physical layer, you have the layer 2, and then you have IP, and then you have TCP or UDP, and then you have the encapsulated packets that come as an application layer protocol packet. Basically, and they also contain, so this is the VPN part, and they also contain an IP address, a TCP or UDP. And the core question was, what is more reasonable to apply? Should we apply TCP over TCP? Should we apply UDP over UDP? Or TCP over UDP? Basically, which of these two to select from here? What is more reasonable to select? And the observation is that TCP and TCP together do not comply well, because TCP has a property to adapt to the available bandwidth availabilities in the network. So here typically in IP, in the multi-hop connectivity, there's some unreliability. The buffers in the routers on the path are sometimes congested, so therefore the bandwidth, the sending bandwidth should be adopted. And if this TCP, basically it has this tooth saw characteristic, it drops, and then it would try to reach the potential maximum again. So in this dropping might be interpreted by this TCP again as a further dropping So some kind of congestion. So therefore, they even react probably even further and stronger. So if you have one TCP that's sufficient to provide for adapting the bandwidth to the multi-hop network path, and having two would interfere with each other and would lead to a lower bandwidth utilization. So therefore, what is recommended is to use a UDP, which just tries to, as IP just tries to deliver the message drop might happen, but the TCP at the higher layer can compensate for that. Okay, yeah, this was the summary. So in practice, it's even 50 to 70% less throughput that we have with TCP over TCP. So it's due to this additive increase and multiplicative decrease. That is characteristic for TCP. So typically, for every amount of packets that have been received correctly, you increase the bandwidth additively. So you increase and increase until the first messages, let's say, you get an information that messages are stalled and that they should be resent, then it's dropped multiplicatively to the half of it. And then it tries to additively increase again and then drops again. So it has this tooth-saw function. And if you combine two tooth-saw functions, so this drop would be considered as a further drop in the other TCP. So it's just called nasty interaction. So, okay. So let's see what kind of typical tunnel solutions they are. Probably you also use sometimes some on your own. So on the one side, OpenVPN, for example, cross-platform, you can tunnel over TCP or UDP. Very flexible. There's various solutions available. What I'm IPsec. Okay, so this is more for. Yeah, this also offers layer 2, layer 3 tunneling. IPsec is a protocol that also is supported. There are some tunneling elements over SSH, SSL, or TLS encrypted TCP connections. So sometimes what you can also do, especially with SSH, you can create secure software shell. You can, typically this is used that you log into another machine and then you can type in some commands in the Linux shell. But what you can also do is to create a reverse connection where you basically say, this is my machine and I connect to a specific other host. So this is remote. And I create, how is it done? Let me just see. Yes. So you expose some kind of port, let's say port 1234, that you can open, and every message that is sent to this port can be directed to your machine. So you could, for example, by this, if you are a remote worker, yeah, you can really combine any kind of option. So you could be a remote worker. You connect. So let's say this is the server. Let's draw the remote worker somewhere else. And then you connect to the machine, but you also create a port inside. So let's say this will be port 1234, and all of your programs that access your local host 1234 will be pushed out at this machine. That you can also do. Or what I personally also like quite well is Tailscale. Do you know that? That's some very nice tool which is simple to install on all of your machines. And you can basically select, maybe I have an example here. Yes, just how to put it. I'm just trying to shift my, I will do it differently. So, yeah, I can just see it on this screen. So basically what you can do is you register on all of your machines that you have. So you can install it on your smartphone, you can install it on your on your notebook, on your server at home, whatever you have, and it allows you to configure for every of these machines what the output, what the exit node should be. So this you can really run by your own. Let me just see whether, so this is how it looks like. You can have various machines that you have registered, and you can select on which of your machines you want to have the exit node. So you can also, for example, select that your smartphone should be the exit node for your notebook, or your notebook should use as an exit node some server at home. So this is very simple to apply. Also with quite low setup effort. And an example that you also had previously is tunneling through DNS. So typically, as I've pointed out, sometimes if you are in a wireless network where you are you only permitted to access some kind of web portal where you can enter your credentials. So what is a web portal? That should be a web portal. How does it look like? Do we have an example here? Is it what I mean? Web portal, is it the right term?
Captive portal? Maybe?
Captive portal, that's better, yeah. Captive portal. Yeah, exactly. So, I don't know. So, willkommen im Schul-WLAN. So you have to type in your username and password, and then you get access to the Wi-Fi. And typically, this kind of captive portals are associated with a URL, with a domain name, with a website name, and this is the only website that you're allowed to look up. But typically, in order to look up the URL file, so you have a URL, for example, myportal.com or fancyhotel.com or so, /Wi-Fi, and in order to get this, to resolve this, you need an IP address. So in order to access it, you need an IP address. And in order to get this resolution, you need a domain name system call. So basically, you have to send out a request and ask what's the IP address of myportal.com, and you ask an IP address. So the DNS servers have to know by DNS by IP address. You cannot use URLs there, and it tells you, okay, the IP address is 1234, and then you can send HTTP query to 1234, and you get the portal, with the password and the username field. So, and no other website are permitted typically. And what you can do is to take the chance that this kind of communication is free. So in this DNS request, you can ask one DNS server of your choice. You can send requests with your, basically asking for the content, for the IP address of specific portals. So how is this typically realized and implemented? Typically you have a firewall, which you are on this side, and DNS is allowed, so to the internet. Then it is allowed to access the captive portal, and everything else is blocked. Before, of course, at one point when you enter your credentials in the captive portal, then the firewall can be configured to allow you to pass your regular traffic also to the internet. So these two connections are allowed. Here you do not have so much gain. If you access the captive portal, that's what typically is expected of you. But what could be an attack, let's say, is to use this possibility to regularly communicate to the internet. And how can this be done? Just by tunneling. So you select one of your own. So of course, you need to have a server with an IP address that is publicly reachable, and you install a specific DNS server that is not a real DNS server. So basically what you do is all of your IP packets that you have are somehow packed into a DNS query, and is sent to your own server. Your own server will unpack it, send further forward the IP address, get the response from, let's say, the website you want to visit, and sends the response back, also embodied in a DNS response. And because the firewall doesn't really check how many requests you send out, you can just simply communicate, send out more requests, more responses come in, and you can put in your traffic in that sense. So what can you do? So communication over the DNS tunnel between client and a prepared DNS server works as soon as you are allowed to resolve DNS host names. So you can really circumvent this kind of, or let's say differently, an attacker could circumvent this kind of captive portal and use the Wi-Fi also without, let's say, permission, and just look up the websites that you want without interacting further with the captive portal. So from the defender side of view, there's always, you need to always model basically what throughput, what kind of permissions are still granted, and consider how this can be misused and what assumptions are made and whether they are valid or not. Okay, let's look into some other kind of potential attacks on the internet when we are currently at it. And let's look at very simple denial of service attacks. One of the core security goals that we have, so have confidentiality, so authenticity first, confidentiality and integrity. That's mostly focusing on objects, but we have also availability. And from the attack, so how's availability defined? It's basically the availability means that no authorized and authenticated user. So the trick with security definitions and security goals definitions is often that they are twice negated, and they have a reason. So availability. Do you remember how availability is defined? How did we have a look at it? So the traditional thinking that you could have would be, one moment, that would be system is always online. System is always online and accessible for authenticated plus authorized users. So this is the positive statement. It's always online, always accessible. But typically these kind of definitions are twice negated. So that means a system, or let's say an authorized, authenticated plus authorized user must not be, so first must not be stopped, affected, must not be, let's say, stopped in its ability to access a system by an unauthorized, let's say by an attacker. So what's the difference? Do you spot the difference? So if you define it positively or you define it negatively? So somehow this stopped is the second negation. What's the difference? If in the first you claim that it should be always online and accessible for an authorized authenticated user, or whether an authenticated authorized user must not be stopped in its ability to access a system by an attacker or unauthorized user. Is there any difference? Okay. So we are about availability. So what we want to achieve is that no unauthorized, authorized and authenticated users must not be stopped in their ability to access the system by an attacker. Okay, so let's say an attacker would like to achieve this. Which and what kind of systems do we talk about? So somewhere there's an internet, and let's say there's a server accessible. How would you implement an attack? What could you exploit? So what, and you know this is running on a machine, what kind of limitations do you see in the machine that you can, in very generic sense, use to your benefit to try to stop other legitimate users to use the system? And then we have to look into how typical network stacks are set up. So one element would be if you have a system, what you can do is, let's say, on the path to the system, so this has some specific IP address, what you could try to achieve is to modify the routing table of the devices that they try to route it somewhere else, where the original system is not located, so you do not, so the traffic from outside doesn't reach the original system. Another element that you could do, it's written here, is to overload the system. So typically what you have is you are listening on one port, and when a message comes in, let's say this is a TCP system, so it uses TCP. What you require for TCP is the whole state, that you are able to, there are the sequence numbers. You need to establish a state for the sender and you as a receiver, and which ports are associated, so that you keep track of the sequence numbers in both directions, that you keep a buffer for the, so let's say sender A for sender, and then you have a sequence numbers for this connection. So typically for every connection you need to set up some kind of state. And what you can do is, at the attacker side, for example, to create so many calls, so many requests, so many TCP connections, that this kind of state is using up all the available resources, and legitimate users, so they are all bogus, they will not be maintained, they will not be answered by the attacker, but they, for one period of time, will consume resources at the recipient side, at the server side. So, and if a legitimate request comes in, then they might be not anymore further capacities to maintain this connection. So what else can we do? We will look into various options how this can be done. But the core question is a very simple one. So if this is an attacker, and this is the server that it wants to attack, what it wants to achieve is obviously to make it more harmful for the server than for himself. So if you invest, let's say, $1 here, or €1, or one energy unit, then it should be more energy units or dollars that are consumed here. So it should be somehow asymmetric, that you have some kind of leverage, so that for every amount of energy that you invest, you get the 100-fold effect at the server. If it would be 1-to-1, then you are basically, then you are destroying. I mean, then you do not win anything, because you just, what you lose, the other loses as well. So it's stalemate. So it's not really worth it. So the question will be, how do you create an overload with the minimum utilization of your own resources that is difficult to identify and difficult to block? So you want to have some leverage. You want it difficult to identify, because if it's identified, then countermeasures can be activated. And let's say even if it's possible to identify, then it should be difficult to block, because blocking would also harm legitimate traffic. No. I don't know why. So for example, I mean, obviously, let's say at airports, you could have some threats incoming, yeah. And if you want to block the entry at airports, you could of course shut the airports down, but that would also stop legitimate traffic and passengers passing by. So you need some kind of mechanism for blocking that filters out the malicious ones and permits the legitimate ones. So how can you do this? So first have this leverage effect, asymmetric resource consumption. You spend 1 unit of energy and the victim has to spend a magnitude of that. Once this is achieved, then you could try to increase your own resources. So of course, if you have, let's say, a leverage effect of 1 to, I don't know, 10, and this is the server, and then you apply further activities, then you also increase your leverage by just more participants in the attack. If you would have more resources than the victim, one-to-one relationship would be also fine, but that typically is rarely the case, that this is somehow, then it's too easy. I mean, this is then not complicated. Okay, so let's have a look at how we can have this leverage effect. This will be one in the focus, and there are different examples how this can be done. A SYN flood, a Smurf attack, or DNS amplification. Let's have a look into this. So let's start with the SYN flood. So this is what I showed in the first slide. So there you have a TCP based system which is waiting for incoming TCP connections. And again, as I said, every TCP connection that is open requires some resources. What do we need to store in this context? Because a TCP connection is a connection-oriented protocol. So you need first a handshake to agree at least on the sequence numbers in both directions. So you have the sequence number in this direction, sequence number in that direction, because TCP makes sure that every packet that is dropped, that is somehow getting lost, is resent, and the orders are correct. So for the ordering, you need a number for every packet. For the packet loss, you need a number for every packet. So basically, you have sequence numbers in both directions. And you also, a little bit network state, but also the address of the contact partner. So you need to store something. So it's not like UDP, where you just accept the packet and then you deliver it to the applications that it's associated to, and you don't have to remember anything. Here you have to really remember where in the communication you are currently at. And this kind of state takes some storage space and some memory space. And what you could do as an attacker is to say, I want to connect to you. You send a SYN request, so the TCP handshake starts with the flag synchronize, enabled by the sender. Then typically there's and also it sends its own sequence number, and then here's also synchronize, and the sequence number here is acknowledged, and the own sequence number is sent, and then the sequence number, this is also acknowledged here. So this is the typical handshake, and by this both parties have exchanged their sequence number and both have acknowledged that they have received it well. And now with both sequence numbers established on both sides, they can start sending the packets and numbering them, bytes in them. So it's easy. But what happens if you just send this first message and you ignore these? So the server will answer, but you do not send your final acknowledgement. So basically it will stop here. What happens then? The server thinks the connection has been established. Yeah, the server No, it has not yet really been established. So here it's waiting for the acknowledgement, but it's waiting, and there's a timeout for it until when this acknowledgement can arrive. And during this timeout, the state has to remain in the memory. And what was it? What did it cost for the attacker? Just one message, and it generated and it caused some state to be created at the server side. So you send a SYN packet to the server, you ignore the response, and repeat this frequently. Yeah. Why is this a good denial of service attack? A moment. Any idea? Okay, I mean the idea is that let me just see, because there's also so-called HTTP. Okay, so the idea is so the cost imbalance, the leverage effect for the sender is much. The leverage effect is quite high. So what happens is that you send just one single message, but the amount of work that the server has to do is much larger. And just frequently, so there has been very similar attack also in HTTP. I will quickly have a look. So just what is the effect before we come to the stronger element. So the server has an increasing number of half-open connections. For that, it needs to store states or resources. The attacker doesn't have to do anything, so it just sends continuously new sync messages. And once the states at the recipient are somehow consumed and a legitimate request comes, then because there's no space for further state to store, the new TCP connections are rejected for other clients. You could also, and that corresponds, this kind of attack also corresponds very simple with IP spoofing. In IP, you can select your sending IP address. You just can claim to forward it for somebody else. You might act as a router. So the original sender IP address that you select can be random, and because you anyway do not want to have the result and the response that you would not get, you can obfuscate your identity. So it's even make it more difficult to filter and to identify. There's been also very similar. Before I come to this point, still continue to this. So what can you do? So what can you do to counteract it? And that's a general recommendation for preventing denial of service attacks. What is the core problem? The core problem there is that this state about the connection, especially the sequence number of which is sent in the first message. So typically the first message tells you, I'm sending a sequence number and I am from IP address A. This is what you need to store. The sequence number associated to this message. So port X. So these two. The IP address, the port, and the sequence number. This is some unit that you need to memorize at the server side. And what can you do? You shift the burden of remembering this to the sender. So you do not remember it. So what you want to do is to receive from IP address A and port X this SYN and sequence number, and you want to respond also by SYN and your sequence number. So sequence number, how to say it, this from A and this is from B, and all of this information you want to put somehow in the message that the next time this is acknowledged, you get that kind of information back. So you didn't have to remember it. So what do? So again, what's the unique identifier for the connection? The IP address of client and server, the port number of client and server, let's say the time of the SYN reception that you can somehow associate whether it's the timeout has occurred. The maximum segment size, that's right, that's also in that message. Initial sequence number. So basically this is the elements that you get with your first handshake. You do not want to remember this, but you want to send it as a cookie to the client in a way that once the second message of the sender of the message initiating sender is received, the cookie should be delivered, and you should be able to verify, yes, this is a cookie I created, so therefore I trust the entries that are in it. So I didn't have to remember, because if the second message from the sender, all the information that I should have remembered are now presented to me. So how does the cookie get to the client and back without assuming a new TCP connection on the client side? Any idea what you can do with it? How can you create this kind of information that contains these elements, that what you should have remembered, and the verification that the cookie is from you. And you cannot create new messages. So the trick is also on this slide that you send in this second message, the SYN and sequence number B. This is what you sent, so it must be contained in this message. And you are not allowed to add any more information that you have there. So how can you do it? The only data field the server is free to choose for this response message, again, so this is the SYN egg, and here the cookie should be presented, so this is the egg. So the cookie should be somehow here, and here it should be again presented. So how do you take it? So the only element that you can modify in your answer message is a sequence number. So this is your sequence number that you present for the other sender to use. Yeah. And how large is the sequence number in TCP? Let's have a look. Any idea how much information we have? So it's a 32-bit sequence number. So we have 32 bits. So what do we all encode in it? So we have 5 bits for the timestamp. Let's say, okay, we give it 1 tick is 46 seconds or so. It's not very precise. You can make it more detailed, but that's fine. The maximum segment size, this is how large the message can be in bytes. 3 bits, that's very, very small to encode in it, but let's say you have 512 as a basis, so 1 bit, so 000 would be 512 bits, 001 would be 1 kilobyte, 010 would be 1/2 kilobyte. I mean, you can create such kind of schemes. So it's also acceptable. And then you have a cryptographic hash over the IP address of client and server, the port number of client and server, and the timestamp. So why is this? This is because you want to verify that you created it. Yeah, this cryptographic hash is using some kind of secret. So it's very often a typical encryption mechanism for symmetric encryption is that you hash by taking the message, so this would be the message, and adding some kind of secret key that you have. And by doing so, nobody can recreate a hash that does not have this key. So the next time the sender acknowledges your message. What is an acknowledgement? An acknowledgement is also a 32-bit number, and it's typically the previous sequence number plus 1. So basically, yeah, I don't want to go much into detail. So typically in TCP you have this byte stream and with consecutive bytes. So they are typically, these are the areas where you create your blocks. This is the maximum segment size. And let's say this is segment number 0, and then you have 1500 bytes, so it ends at 1499. So you count typically the bytes. And let's say this is the packet that you received, the bytes from 0 to 1499. So the sequence number that you would acknowledge is 1500, meaning I'm now expecting from the byte 1500 in the byte stream as next. So basically it's associated to the sequence number. So if you send this as your sequence number and the acknowledgement is referring to it, you can recreate what sequence number did I use that time, and you can check with your secret key whether you created the message or not. So if you take the message that you received, you add your key and you get the same hash that has been sent, then you verified that you are the original author. So what is the trick? The trick is to put everything that you have, everything that you would have been required to memorize in the response, in your sequence number that you use, and once the acknowledgement comes, you can verify that everything has been correct. And the second answer of so basically this acknowledgement of the sender is really belonging to some previous request they had sent. Okay. I wanted to show you one example of how this kind of TCP connection establishment is also working on other kind of protocols. So here you see a so-called HTTP 2 rapid reset. It's from 2023, not too old. And the idea was, it peaked in August 2023. And the idea was that in HTTP 2, so this is now not anymore TCP, but in HTTP 2, you can also create within the protocol multiple streams for different kind of multimedia traffic. Yeah. And that was HTTP 1, so you could just one request, one response. Let's open it in a new image. Okay. Then HTTP 2, you could send, let's say, magnitudes of requests at once. But you see, you still had the same amount of effort. But now in the HTTP 2 rapid reset attack, you could. So previously, let's say the servers were limited to only accept 100 responses from one site. Yeah, this is the image in the middle. So HTTP 1, you can send one request, there's one response, and then again you're allowed to send a new request. So you're limited in the frequency of requests that you send. In a standard HTTP attack, you can send up to 100 requests at a time. But if you would send 100 first, the connection is stopped because you are an attacker. So therefore, the attackers had to adopt and only send 100 requests at a time, consuming a little bit more effort. Okay. And now this HTTP rapid reset attack was, you send a message, I want to establish a connection to you. The server starts creating the connection, the state, and then you reset it. The red messages are the resets of the previous connection that you just established. So the server starts creating the data structures. Then it gets the resets. Oh, it has to build them down again. So you first have the effort to create the connection at the server, to establish the state, and then you have the effort to garbage collect it again. You have twice the amount of effort, and the sender can very easily just send requests to establish the connection and to stop the connection. And at that same time, just simply generating more traffic to the server. Okay, let's have a look at another kind of attack. Okay. Okay. So what do we also have? So okay. So we can also have a so-called Smurf attack. Okay. One moment. Here we have some physical attacks on my setup. Something is not going well. Let's see. As long as it's recording, that will be fine. Okay. Okay. So, what is the main idea? So, we are now in a kind of network where we have this is a network that is connected via router to some other networks. So let's say here other networks. Sorry. So just think of a network with various hosts. They are connected to a router. This router is connected to another router, which is connecting to another router, and here further hosts. So you could have here, so this is router 1, this is router 2, this is router 3. And then you can also assume this is somehow at the university. Previously, in the past, routers forwarded directed broadcasts by default setting. So, for example, if we have here the net ID of, I don't know, let's take this of the university, 93881, and the highest IP address 255. So if all so if this is the host ID all once, that means it's a broadcast. And typically the routers forwarded the message. Okay, so let's say this client sends a message to this IP address, so the regular routing takes place and the message arrives at R1, and that's broadcasted for a subnetwork, which is not the sender's subnetwork. Yeah. How can this be used as a potential attack? Also, you can also have this ICMP echo request, packets that they received via broadcast. Oh, okay. So, attack part number 1. This host here, down here, can send a message to the IP address associated to this network, subnet, so that it should be broadcasted in it. Yeah, so its message is delivered to the network and they're broadcasted. And the second, they can also send ICMP echo requests. Do you know what ICMP echo request is? Very simple. I think so. ICMP Internet Control Management Protocol. So it helps. It's a part of the layer 3 network layer, and it helps to maintain the status, to communicate the status of the network. So what you can do is to ping a website, and then you get a message is sent there. ICMP message is sent there with the that's an ICMP echo request, and then we get the echo reply, and then we compute the round trip delay. So basically the message going there and coming back. So it takes 8 milliseconds, 12 milliseconds or so. We can also go a little bit further. Deutsch-Kasachische Universität in Kazakhstan, so that we have higher. So basically we ask the recipient in this case to answer us back. You see here we had, in this case I think, so we started with 64 hops, time to live, and every hop decreased it, so we had probably 9 hops, and to Kazakhstan we had roughly 18 hops. Okay, so how is it connected to the message, to the attack? You could send an ICMP, ICMP echo request to the subnet. Any idea how you can use it for malicious purposes? So this is 2. Yeah, sorry. This is attack option number 2, and let's say attack option number 3 is IP spoofing. And if you combine this, you can do something bad. No idea. Okay, you're very well behaved and benign people, not thinking of anything bad. So let's see what you could do. So let's say an attacker is here, and here's the network that is supporting broadcast. So if the router, so let's say this is our local network. So 0/24. That means if the host ID is 255, all bits in the host ID are 1, then it's a broadcast. So let's say this attacker is connected through some router to this net ID. And let's say we have here a critical server, mail server. And it has the IP address 143.93, let's say 82, so it's in different let's say this one, doesn't matter. Okay, so what can we do? So the attacker creates an ICMP echo request. Sent to this broadcast address. So this is the recipient, and who should be the sender? From 1482 from the mail server. So this is the message that the attacker creates. Nobody will verify its source address. So it sends this message, it goes to the router here, because this router is routing the IP addresses for 143.93.81 and everything inside, including 255, which is the broadcast address. So what it does next is it broadcasts it to all of the members within. So what message do all of these participants in the subnetwork get? They get a ICMP echo request. Please answer me back to the mail server. I want to know the round trip time to you. Let's say here 200 devices. All 200 devices send their reply back to the mail server. That's a very nice amplification. So you just send out one simple message to one simple broadcast address, and the whole network within associated to this is responding to your victim device. And depending on if the firewall allows it through, then now this mail server is getting quite a lot of traffic. And if you send this ICMP echo request to some other subnets, then you increase the bandwidth towards the mail server, and legitimate requests might be delayed so much that they are not responded correctly. Because the mail server is now starting to process every individual reply, it has to send them back, it has to consume its upload bandwidth as well. So it's quite effort that you have caused. So what is the main idea? You send an ICMP echo request as directed broadcast, use the IP address of the victim as a sending address. That should be so. That's a so-called reflection attack. The other attacker doesn't communicate directly with the victim. The exploited systems are so-called amplifiers. They attack amplifies the attack many times over. So very simple amplification. You consume the resources of the victim. It has to process every message individually. So how can you protect against it? To not allow directed broadcasts, because the legitimate use case is very small. To have firewalls. So for example, if in the previous case the attacker would have passed a message through firewall and it would have faked its IP address, then the firewall could have said, that's not true, you cannot send from this source address because it's not associated to the network I assume behind this, in this domain. So if the firewall assumes a specific IP address range in this domain and something else comes out of this, then it's considered malicious. And also, the group of hosts answering to this ICMP echo request, they also get as an IP address, as a destination, the forward, the broadcast address. So they see this is not individually meant for them. This is a broadcast address. So you should not respond to those kind of requests if it's for broadcast. Okay. What did we learn now? So basically this reflection attack. So basically you ask a different group with your attack to attack your victim. So the attacker asks the reflection group to participate in the attack without them knowing that they are participating in an attack. Okay, another similar setup where you also amplify, where you also use an indirect attack is a DNS amplification, where the regular use case of DNS again is DNS server, the domain name system. You give an URL, typically a domain, and you get the IP address. So this is the core functionality. And how is it typically done? Typically it is done that this is the attacker. Okay, so let's say a regular client. Let's say this is a regular client. There's a DNS server. You ask what's the IP address of Heinrich University of DE, and you get an IP address. So this is the typical use case. Typically the request is such small, so you just have a source information, you have the destination IP address for the DNS server, and you ask the domain, what entries do you have? And you want all of the entries. And then you get all of the entries. So let's have a look how this looks like. This is one short question answer. I get an IP6 and IP4 address, and I think, let me just see if this is correct. Not really sure. That's not something that I was expecting. So typically you can also get further information. Let me just see what the right syntax is. We can also do it this way. Let me just see. Do I have here some more information? Yes, yeah, okay. So let's take here regular NS lookup service. So you get the IP version 4 address, version 6 address, some TXT records. In this case, this kind of information is written here. This is somehow to verify something for Outlook. Then you have further name records of the managing company. You have the email address. So the mail server is dedicatedly also entered in the DNS entries, so that if you want to send an email, the corresponding server is also named. And then it's stated who has created the entry, how long is it valid. So this is typically what kind of information you get. And yeah, I was hoping to get some more information, but okay. No, okay. Type any. Yes. Maybe I can still do it in the short time. Type equals any. Okay, so this is the full information that we get. And you can compare, I mean, IP address, sender, source and sender, and a very small URL, and you get a much longer answer. So what you typically can do is to try to amplify that. So basically to see for which URL, which domain do I get the largest response. Again, combined with using a fake source address. So here the source address, I'm not sure, did you notice? The source address here is not corresponding to the one of the attacker. So it's somebody else's source address. So if you again spoof your IP address, you just take the IP address of your victim, you send a small request. You will not get the response, but the attacked node will get the response. So then typically the challenge here is how to get the largest response. So this is somehow not so large. Let's say if you get something larger. This should be much larger, but I'm a little bit confused because it's smaller. So you sometimes, as an attacker, can have the challenge to find IP domains with larger responses, and then you just send these responses to somebody you want to attack. So how can you prevent that? So one of the core elements is that you okay, so here it's written recursive DNS resolvers and also open recursive DNS resolvers. So DNS can be implemented in two ways. Way number one, if this is the attacker, it asks the DNS server what is the IP address of, let's say, Graffi.de. Then either, if it's recursive, then the DNS server looks up who knows about the domains of DE, and then let's say who knows about Graffi, and then they respond you back. This is one way. The other way, and this is which causes basically the trouble, because this is the only point where some kind of activity is required from the attacker, and then the amount of work accumulates that is then sent to the attacker or to the victim. And the different approach would be to have it iteratively. So basically you ask who is the IP, what's the IP address of this domain, and then you get back the response, ask this DE guy, and then you ask this DE server, what do you know about this domain, and you get some further clarification. And then you ask that server, and then you get another response. So basically only in this last step you could redirect the traffic to the victim, and as you see, you would increase the amount of work for the attacker. Obviously also preventing forgery of the sender address, more verifications. TCP should be used for large DNS responses. Why is that? So if DNS is used, typically they're using UDP. UDP has no handshake. Why is it using TCP blocking the usage of IP spoofing? So why is this not going well with TCP? Any idea? So let's have a quick look. Do you know? Yes. Mm-hmm.
So you have to get integrated connection and so if you don't have a broadcast connection or broadcast TCP connection attack, then I think it's again the one-to-one scenario. So if I want to attack a system with TCP, must have enough resources, or as many resources as the system has. And
Yeah, that's also, I mean, yes, you cannot broadcast TCP, that's right. But here the goal would be to use IP spoofing to basically create a big message, a small request, a big reply, and the reply sent to the victim. But why cannot we use IP spoofing with TCP? So DNS typically uses UDP. UDP is very simple. You create a request, you send it to the server. That's it. And the server responds to the respond to source address. Yes, please.
You mean the response, another client will get the response to the handshake?
Yes, exactly. With TCP, you require the handshake before you even send the request. So first you need the TCP handshake, and then you can send your request. Shake, yes, and then you send your, let's say, even this DNS. So this is the first, either here or you have it afterwards, doesn't matter. But what is important with TCP, you first need to receive the first response. So this response of the server is essential to be processed correctly. Otherwise, you cannot send your next message. And because in IP spoofing, you do not get the response, the victim would get the response. This basically stops then here, so you get this, but because you don't get the response, you cannot send the actual request. So using TCP stops the IP spoofing problem, but it introduces the handshake delay. Okay, so very generically, what can we do? So let's say very generically, a problem of denial of service attacks is if you have a service where providing the service if it costs you more than the user, then you are vulnerable to denial of service. That means if you are doing more effort in providing the service than the requester does, it's will be misused and will be used against potentially you. So number one, the service requires negligible resources. This is like with the SYN cookie, that you do not remember anymore what you should remember. You just put it in a package and tell the sender, please, next time you access me, provide me this package. I will verify that it's for me, and I have all necessary information that I need to remember in this package. And it's your burden to carry it. Offer the service only to a closed user group, yes. And especially if they are authenticated, you can trace back individual actions. So typically if you're interacting with anonymous users, then everything might happen and they might misuse you. And but if you have a closed user group where you in the best case also have them all authenticated, you know who you are dealing with, then you can trace back attacks to those. Increase the resources required by the user, so you make it more difficult for the users. Then you get the legitimate users will still pay it and do it, but the attackers will not. Yeah, and maybe TCP breaks IP spoofing. That's also good. So for example, also for email, it was once discussed that there should be some proof of work. So somehow you calculate some difficult calculation that takes you 1 second, 2 seconds, or even 5 seconds for sending an email. That's acceptable for regular users. But if you have spam senders that push out the emails all the time, then for them that would be more difficult. And sometimes, okay. Yes, now coming to proof of work for the emails. So sometimes it has been proposed that in order to increase the cost at the user side for requests that you want to limit, but only for those who send out millions of requests, you can introduce some kind of proof that the service user has consumed, he has consumed himself. So if you have this imbalance, let's say the user requires one resource and it generates 10 for you, then you increase some artificial costs. Yeah, you give it some additional costs so that for the user it's more expensive. So it's not so easy for them to ask you for the service. That's okay for every regular user, but but makes it difficult for regular attackers. So especially computing time. So just assume you would require 3 seconds for every email you send. That's okay. But if you want to send thousands of emails per minute or per time unit, then it's 3 seconds are more problematic. So you can also set a task for the service user whose solution is computationally intensive. It cannot be parallelized, but the solution should be simple to do. Yeah. So, calculating square roots, hash collisions, many more. So hash collisions would be if you have a hash. So Bitcoin does it very similarly. So in Bitcoin, in order to create a new block, it is required that you hash some previous content, and the last bits should have a specific pattern, maybe be zeros. And let's say you only require the last 5 bits to be zeros, then you still have to, so you can add a random element here. You still have to try various random elements in the otherwise fixed set and to hash it and to have a look what comes out. And by chance you will find a value which ends at 5 zeros. I mean the chances are 100,000 to 1. So you have an average to compute, I don't know, 100,000 hashes, and if you want to make it more complex, you increase the numbers of zeros required. So it's easy to do. Okay, so that's especially that what also Hashcash was proposed to do. Basically, it introduced as a protection against spam. It introduces an additional line into the header of the email here. And this is the random element. So everything else is fixed, so that that's nothing that you can change. But what you want is that with the cryptographic hash function, let me just see. Yes, it requires that the additional header line has a partial collision with the 0 string in the first 20 bits. That means that if you hash this email combined with this pass hash, then some part it should result in 0 in the hash. It's exactly that, because you cannot predict it. So hashes have the property that it's very simple to put something inside and then you get a hash, but you don't know, but you cannot redirect. So, and you cannot also identify. So especially this going back is very difficult. So if you have a hash, let's say with the property that it ends to various zeros, you cannot go and find a corresponding M. That's impossible. I'm not sure whether we mentioned this, how the core idea of doing a hash is. So hash, what you could do is you take the message and you just consider it as a cryptographic symmetric encryption. So you encrypt the message with the key, the message. Yeah, so you take the message as a key to encrypt the message. It's a little bit strange, but you get something of a fixed length out. So let's say 160 bits. This will be the hash. And without the key, I mean, which is the message, you cannot go back to the message. So this is impossible because you don't have the key. And if you have the key, you have the message, you apply it, it's simple to compute the hash. So this is the core idea somehow. So therefore, you cannot get a message. That's like having a I don't know, some kind of some encrypted element, and you want to find. Yeah, it's just so. You are just bound. So you just have to try out different amps, different elements, in order to find something that ends at 20 bits with zeros, let's say. So all what you cannot do. So what you cannot do, two input values produce the same output value. That would be a collision. So that would be if the hash of M and the hash of, I don't know, K, another message, would be equal. That's a collision. A partial collision is if they match some of the bit positions, especially with the zeros. But checking is very simple. So if you have M, you can simply create the hash. If you have K, you can simply create the hash. But what is very difficult is, sorry, not this way. This is very difficult. So if you have a hash, to compute what message it comes from. So this is a very simple mechanism to cause some effort. It's as similar, as equally as in Bitcoin. You just say find a random bit string, so some string or so, that you add in this header. So if the hash is created from this header fields, or maybe also the whole message, the hash has some specific properties. It ends with 20 zeros. Okay, finalizing. So we just finalized this chapter on network access today, and we looked at network architectures, especially what you should keep in mind. Yes, how to organize it. Typically, that you have the internet, you have sometimes demilitarized zone, and then you have the internet, intranet. Then you have various firewall types in between. You also had application layer firewalls such as proxies. We also, okay, it's proxies, yes. Intrusion detection systems, where we saw the various rules that can be applied that are very, very simple. They look in every packet, and they look for specific patterns. Then we look for tunnels and VPNs, which basically just take your IP packet that you would have otherwise sent to the outside world, to the internet, put it in some kind of carrying material, DNS or some other protocol, sends it to the end host, to the recipient, and then it's unfolded, unpacked, and released in the local network again. And we had to look at denial of service attacks. I just want to give you some short outlook at what we will cover the next lecture. I think we already started and somehow in the exercise. We're a little bit early with the exercise. So we'll look at steganography and how network communication can be basically hidden in plain sight. Yeah, maybe just one small motivating story for that. One very historic anecdote how this was used. So first of all, steganography covered writing. So it's hidden writing, practice of undetectably communicating a message in a cover object, something that looks normal but contains a message. And there's a nice story about a Greek tyrant, Hystaitos, who wanted to send a message to, I think, his brother or his brother-in-law somehow, to coordinate an attack on a rivaling city. And he wanted to pass that message to the other city, but he knew, okay, on the way to that city, there are various checkpoints controlled by the enemy, and they will check the slave for any kind of messages that he's carrying. So what did he do? He shaved the head of his slave and wrote a message on his head, tattooed it in, and that slave had some property I cannot repeat. So his hair grew back and covered the text, and so the slave was free to go and show that he didn't have anything on him. Obviously, the slave also was not allowed to see his own head and had to carry a scarf during the regrowth of the hair. And then once the slave passed over to the other city, the head was shaven again and it could be read. What also is very nice is, let's say I like this one. So this pattern in the, it's difficult to see, but let's increase. So this is some wool. It's very difficult to see, but I hope you can see some more tiny dots. Here's a dot, and there's a dot, and there, and here some. It's some slightly imperfections, as you might assume, but these are dots or lines, and this is some kind of Morse code that you can put into your scarf, and it writes, "I will always love you." That I found interesting. And this is also very nice. This is from some NSA photos of German spies, how they communicated with. So you see there's some messages hidden. I mean, there are some blacked letters that you cannot see the text, but the black parts of the letters are not the code. So what you can also see here is that you have here a black dot, there a black dot, and there, and in the corners you have the black dots. So here, for example, and here, and over there, and these black dots are coding the information that you need. And sometimes if you play poker cards, what you can also, of course, observe is if you have some kind of cards. Yeah, this is the typical classic. Let's see. So if you play some cards with some people who know the trick. Oh, this is maybe even better. This is where's the picture? Just to yeah, exactly. No, this open image, a new tab. Yeah, come on. So here you have a regular card, and it has some nice fancy pattern. Yeah, and depending on over here where there's something missing, sorry, it's depicting the hidden symbol of what card it is. And over here, sorry, and over here on the left you see whether it's hearts, spades, or clubs, or diamonds, depending on what's missing. So and if you don't know what to look for, sometimes I would also assume that this kind of grass, whether it's smaller or higher, somehow signals the information. So you could have information hidden in various spots, just to keep information hidden. Yes, so that's what we will look into next time, and happy that you have been here today. So see you next time in the lecture. Have a nice day.